behalf of myself and Bala, my co-chair at the Analytics Network, thank you very much to everybody for coming this afternoon. And thank you very much for Dolores Romero Morales for coming to talk to us today about her really important work on helping to make AI a bit more transparent and therefore a little more fair. It's something that I've been really excited to listen to, and from the amount of participants we've got turning up today, I think all of you are as well. So before I kick off, can I just ask everybody to please consider, if you have come today as someone who's coming to this free event as part of the Analytics Network, please consider joining the OR Society. We can't continue putting on great events like this and having lovely people like Karen working to help us put on these events and make them what they are and publicise them in the way that they do if we don't have members of the OR Society. So please think about in renewing or starting your membership of the OR Society today. You can find all the details on the OR Society pages. And now that I've done that plug, I will pass over to Dolores. Thank you.
Thank you. So let me share my slides. So I am assuming that you can see my slides now. Okay. So first of all, thank you both of you for the kind invitation today. So actually, I used to be in the UK, so it's nice to be back online. Nowadays, I'm working in the Copenhagen Business School, and what I'm going to show you today is basically, say, a research agenda more than a specific paper. So, and as I said, this is a research agenda that I do with lots of people. So today, I'm happy to show you here 3 of the students that have worked with us. So actually the 2 at the bottom just defended their thesis this year, and the one at the top is working with us at the moment here at Copenhagen Business School. There will be also work that I will relate to from many other PhD students. So trying to give the credit to them. So the first thing that I would like to show you is a couple of links to transparency. And the first one that I'm showing you is actually a paper from Cynthia Ruding, a good friend and a member of some of our projects that we have had. And basically, she has a paper in which she talks about the 10 challenges that we are having nowadays in machine learning. And one of the ones that she will touch on is basically the transparency of the algorithms. This transparency, I always like to make it extremely clear that it's not something new to us. This is something that, for instance, in certain fields has been required for a long time. And you have there a paper in management science from the beginning of from 2003, in which they talk about transparency in credit scoring, and it's a must. So it was, say, something that you had to do always for credit scoring models. The thing is that with this growth that we are facing around AI, these regulations are being rolled out, widely. And I'm citing here a couple of pointers, say, from the European Union. So this was a paper in which it was related to the GDPR and the right to explanation that it was mentioned in the GDPR regulation at that time. So if you would be, say, a citizen subject to algorithmic decision making, you had the right to ask why this algorithm gave that decision. Now, this is much more recent. It's about the trustworthy AI, but let me move on to the AI Act, which is, say, from 2023, in which they basically list, things that algorithms should satisfy. And again, one of them will be transparency. They also talk about fairness, but there are many others. And this is being nowadays even regulated by an EU center that is located in the south of Spain, which is a center for algorithmic transparency from the EU. And just talking about the EU, but I could talk about other parts of the world in which this regulation is being rolled out. So this has brought us to a whole field of research in which you are not developing an AI tool, but you are developing an explanation for your AI tool. And actually, this explainable artificial intelligence name was taken in DARPA, so the defense in the States, in which they organize several workshops, bringing people from many fields and talking about the need for this transparency. And these tools, as I said, they normally come as a second step to your AI tool, in which you give explanations for an existing methodology. Now, what I like to claim is this this two-step process. We don't need that in our field in OR, because in OR we know how to model these two things in one go with one single model, and this is what we normally do in our research. So I'm going to try to show you some screenshots, just quick ones, but in which I show you how we build algorithms that are trying to do the two things at the same time, to be accurate and to be transparent. And I will try to show you this for different types of data. I'm going to do this, as I said, without showing you the OR model. Sorry for that, but just, give you a narrative to each of them. Much later in the presentation, I will give you a few OR models. And feel free to stop me if something is not clear. So just to start in a very, very simple place, something that we consider to be, say, easy to understand is a tree. So if-then rules. If-then rules are very easy to understand, and then we take a decision in the leaf nodes of these trees, and this decision will be, say, predicting, say, whether you are going to have default or not of a company, or you are going to predict, say, income if we are in a regression task, so classification and regression. So what we did was to write this paper a couple of years ago, in which we tried to summarize all the developments that are coming out from the OR community, trying to optimize classification and regression tree as a global thing and not as a sequential thing as it was done, say, many years ago. And if we do this global optimization of the construction of the tree, then we can impose any kind of constraint that you like by adding that constraint into your mathematical optimization model. And so we have a whole section about what are desirable properties, and for instance, fairness will be one, and then we modeled those in this paper. So this is assuming that your machine learning model is already, say, interpretable by itself. But actually, you may have a model that is, say, not that transparent, and then we will need to do something about it. So I'm showing you here, say, a model that is a tree. So on the left-hand side, you see a tree. And actually, I was just claiming that a tree is interpretable, but of course it would not be interpretable if the tree is so long, right? So if the tree is so long, we have to do something. And what we do in this paper is actually we try to see whether the tree needed to be so long. This is a tree in which we do clustering. And actually, what we do is to try to see whether we can give interpretations to the clusters that are short. And you see me having very short interpretation there, which are if-then rules, and they are short, and therefore I consider this to be interpretable. Another thing that, again, I was talking about trees being interpretable, but we know that we have good behavior, good accuracy behavior if we combine many trees. So now I'm combining many trees. So it's going to be difficult to understand how this ensemble is working. So what we do in this paper is I try to go from this ensemble of trees, I try to go and construct a single tree that will mimic what the tree ensemble is doing. And this is not new. So quite a few people have been trying to do this by using the output of the tree ensemble. What is new in our paper, and we just got this published this year, is that we try to learn good cutoff for my tree that come from counterfactual analysis, and we will talk about that at the end of the talk. So I'm trying to basically have a very sophisticated way of finding what are good thresholds for my tree, and then I build an optimal tree around them. This is another idea that we also have applied several times in different papers, and it's about the type of data that we are dealing with. So here I'm just plotting one single variable, but I will have many more in my model. This is a GLM model, generalized linear model, and this variable is a categorical variable. And I guess that you can see that I have, roughly speaking, 30 categories here for this categorical variable. Now, if you put this categorical variable into your generalized linear model, then you end up having 30 coefficients. So if I would like to understand the impact of this country variable into my model, I would need to interpret 30 coefficients. Now, what I'm trying to do is I'm trying to see whether I really need this very granular representation of my variable or whether I can compact that variable. And what we did in this paper is to cluster these categories. So I have a country variable that I'm going to try to represent this country variable with only 2 clusters. So meaning that if I only have 2 clusters, what I have at the end of the day is a binary variable, whether you are in the first cluster of the countries or not. And you yourself could say which connections are a no-go with, say, cannot link constraints, or you could say also which connections you would like to see. So the clusters I'm constructing, they are flexible to take domain knowledge that you may have. So in this paper we do so, and then we show that in some of the data sets, we basically don't lose any information. This is a little bit of a trickier case of type of data. So before I was talking about categorical data, this is actually data that will come out, for instance, from sensors. So it's functional data. So it's data that we are getting, say, on a continuous basis. And now what we do in this paper is to try to figure out whether I really need to work with this difficult functional data, or whether I could say simplify the representation again from this data. So again, I'm trying to see whether I could simplify the representation and to make it more visual for myself. And what we do in this paper is try to see whether we have, say, parts of the functional data I would like to focus on to get a good accuracy. And you can see that depending on, say, the amount of information that I would like to extract, then I will have different choices of these intervals that I need to focus on. So this is in terms of transparency. Now what I'm going to show you that actually we could also embed our fairness into the construction of our model. But first, I would like to obviously show you something that I'm pretty sure you are aware, is that if you don't carefully train your model may be, say, giving bad results to certain subgroups of the data set. And I brought here with me 4 different screenshots. So on the left upper, you have Amazon. And then what you have is something to do basically with recruitment. And basically, you have a system in which you will be, say, screening a lot of information from the people applying to this company, and there is, say, an unfair way, say, of interpreting this data, and unfair towards, say, women. If we go to the upper right, this is about healthcare, and it's about it's about healthcare in the States, and it's about learning, say, wrong messages from the data, and it's in this case we are, say, discriminating against, say, a race. On the bottom to the left, I have an algorithm that was actually implemented in Rotterdam. And this algorithm was basically about social benefits. And it was an algorithm that it was ranking people. And again, people from certain income, say low, very low income, they were from a certain, again, ethnicity, they were being discriminated against. And actually, this algorithm was taken to court, and this algorithm was basically removed. So it has been a case in the Netherlands in the news for a long time. And on the last screenshot that I have, this is the typical case that people will use in fairness in machine learning. Is about, say, criminals, and whether you will you have to predict whether they would recommit crimes or not, because you would like to give them bail. And in this case, the algorithm is again discriminating against a given race. Actually, I have the data here for that particular case. You have put there the features that the algorithm would be using, and I have put at the bottom of the table the class, and I have a binary classification model in which I have, say, the negative class and the positive class. So if you are rearrested within 2 years, you belong to the negative class, and otherwise you belong to the positive class. So we care very much about a false negative. But then if you train the algorithm, you see that the false negative rate is different for the two races that I have there. So for African American, it will be a 33% false negative, but for white, it will be 14. And this difference is what we will call disparate mistreatment. And it's just one of the fairness metrics that you have in machine learning. Actually, there are many papers written about many unfairness metrics. If I talk about making a model more fair, then I would need to define in advance what I consider to be my fairness metric. So just to be very clear that I cannot claim that my algorithm is fair because it has to be fair given a metric, because different metrics cannot be basically optimized at the same time because they are contradictory. Not because I cannot do from the optimization point of view, but because they are contradictory. You can be fair on one and unfair on another. So I'm trying to make you visualize this unfairness with this plot, because later I will try to give you one, I will try to show you what we do in one of the papers. So in this case, we are predicting income, and you see two colors in this plot. So red color and bluish color, and I'm predicting income for part of the data set, and I see that I'm predicting lower values for the red, and I'm predicting income, and I see higher values for the blue. And you can guess that this is the case in which I have female and male, and I'm predicting, say, lower values of the income because I'm just learning from data in the past. So if you learn from data in the past, we know that this has been the case in the past, but what you don't want is to amplify that effect in the future, right? So you observe that women they have been earning less money in the past, but what you don't want is that becomes, say, what your algorithm is systematically doing. So what we are going to try to do is to try to correct this. So fairness in machine learning, I have a sensitive attribute. I think I gave you several examples. I have gender, I have income, I have race, I may have religion. And if I don't pay attention to this sensitive attribute, my algorithm may be behaving very differently in those sensitive observations as compared to the rest of my data set. And that's what one tries to avoid in fair machine learning. So the references that you have over there are rather recent, and it's basically an area in which a lot of things are coming out. I think I already tried to explain that it's to do with the automation of some of the decisions. So I gave you, for instance, example of Amazon, and it's also to do with the fact that this automation is also implemented in high stakes decisions, which, say, for individuals, it's an undesirable situation sometimes. Just to be very clear, it's not enough that I say that, well, I will remove the sensitive information from the training step, because this sensitive information may be correlated with some of the features that we have in the data sets. So for instance, in the income example I just gave to you, it's also the gender information can also be retrieved by looking at the amount of hours that the individual will work. So it's highly correlated. So I think I mentioned this already, that we like to basically work on the transparency and the fairness and the accuracy being modeled, all of them at the training. And this is what we are doing in some of the papers that I'm going to show you. So the first one that I have is actually showing to you that I could really work just on the data. So my model over here is a linear model. So I've shown you, for instance, a generalized linear model there, or I could have a linear super vector machine, or I could have whatever favorite linear model you have. And what we do in this paper is we try to redefine the data that we feed to these linear models. So what we do is we try to shrink continuous variables. So the tails, I will work on the tails, and I will try to say collapse the tails. And for the categorical features, I do as before. I try to cluster them. And all these changes that I do to the data, I don't do it, say, blind. I do it together with models that are good. So I take, say, a super vector machine, I take a linear super vector machine, I take the coefficients of an accurate super vector machine, and I try to then do this clustering or this shrinking. So it's with information from models that I try to do this alternative representation of the data. And then if you have a look in this plot, you will see that I can reduce the fairness quickly. And if you look at this plot, then my accuracy is hardly affected. In this model, this other paper, what I do is to learn an ensemble of models. What I do is that the weights that I give to the ensemble of models, these weights are going to be fair. So I will try to make sure that when I give weights to each of the weak learners, so say very, very short trees, for instance, I try to make sure that these weights are, say, guided by a fairness metric at the same time that I try to be accurate and sparse. And I hope that it's very easy to see here that if I try to increase the importance that I give to the fairness, I can get to a zero unfairness. I can get, say, to a very good situation in terms of fairness. Obviously, and I don't do this for free. Obviously, there will be, say, a price to pay. So my error will increase. But I hope that you realize that the increase in the error globally, it pays off compared to the dramatic decrease that I have in the unfairness. So I hope this is visual. And actually, what I would like to say is that by doing so, the importance of your variables is also going to change, because now what you construct is the importance of your variables, but for a fair model. In this paper that I'm going to show you now, what we do is something totally different, and I hope you can visualize that is pretty much related to the plot I gave you with two distributions, and the two distributions being, say, apart from each other. So that could also have been the case in supervector machine, where I basically made decisions with the scores. So I give an individual a score, and if the score is high, then I go to the positive class. If the score is low, then I go to the negative class. So if I don't take care of that, then my scores could be much lower for the sensitive group than for the non-sensitive group, and I will be discriminated. So what we do in this paper is try to ensure that our scores get closer to each other. And I hope that you can visualize this with my plot to the right. And in the plot to the left, what I hope you can visualize is that with almost the same accuracy, I could have a big drop in the unfairness. So something that I always claim, that if we do a good search around, say, a good accuracy models, there may be others that have very, very similar accuracy, but maybe I can optimize another objective in that, say, in that area, in that neighborhood of good accuracy models. And in this case, I can optimize, say, my unfairness and dramatically lower it. What we found in this paper, and it's actually quite nice for us, is that we figure it out that by penalizing this difference, say, of the scores between the sensitive and the non-sensitive, what we figure out is that actually we were creating a new kernel. And this is what I was trying to denote over here, and is what we call a fair kernel. So actually, by penalizing this difference of the two distribution, we end up still being a supervector machine with a slightly different kernel. This is another paper that we have written, but now trying to make lasso regression more fair. And again, what we try to do is just bringing more sensitive observations to the upper part of the distribution. And the reason for that is that, you know, you may have a regression task in which being at the top of the distribution is a good thing. So for instance, think about predicting GPA for the students. So that could be something that you do to enter university. So therefore, you want to be at the top of the distribution, you want to be above a certain threshold. And what we do over here is that we control that. We control the proportion, of individuals from the sensitive group and the non-sensitive group that are above this threshold. And then what happens is that, that fairness, we show that fairness accuracy trade-off actually depends on the parameter of the lasso regression. So telling you that basically you have to do this cross-validation of the lasso parameter together with this, not only with by looking at the accuracy, but also looking at the fairness. So I have tried to show to you how we have worked on making different methodologies in machine learning transparent and fair. And I have tried to tell you that this basically will depend on the methodology that you have, on the kind of transparency that you want, and on the kind of fairness that you want. And now I'm going to totally switch gear, but it's still being on this agenda of being transparent. And I'm saying that I'm switching gears because now I'm going to assume that I was given a machine learning model. Yeah, so that model has been constructed, but now I'm satisfying this requirement of giving an explanation to an individual who got, say, an undesirable answer from the algorithm. And this is what people call counterfactual explanations. And I hope that in a couple of slides from now, I show you why we have created this concept of group counterfactual explanations. And I hope I can show to you that by doing group counterfactual explanations, we help the individual who has heard a negative answer from the algorithm, but we also help the machine learning modeler to understand better the algorithm, the model he or she has built. It's a little bit dense, the slides that they are a little bit dense, but we'll skip a few of them. I just want to make sure that because this concept is relatively new and I don't know the audience, I was trying to put a little bit of details to see what is basically the OR behind it. So I told you that I have a machine learning model given to me. Therefore, I have this in the first bullet point over here. And I'm assuming that is probabilistic, but most of the machine learning models that we work with, they are probabilistic. So, and now I am an individual who heard, say, from the algorithm, say, a negative answer. That's what I told you. This individual basically was rejected alone in this plot. And then what we are trying to do is we are trying to construct what we call a counterfactual explanation, which is simply another individual. It's another individual in which I will improve the probability of getting granted that loan. So I'm going to increase the P and therefore I will return the attributes, say, of this counterfactual individual, and then that would be helpful because I will know which are the features that I will need to change if I want to get granted the loan. So I hope it's clear that what you are trying to do is to build a new individual. That's my X individual. My new individual is, say, in the neighborhood of, is in my neighborhood. I'm X0 and I'm constructing the new individual. I would like to maximize the probability of getting granted the loan. So I'm maximizing PX, but because I'm minimizing, then I write a negative in front of it. And I'm also maximizing, say, the effort of me to change from my current, say, configuration to the configuration of the counterfactual individual. So that effort, I call it C, I call it a cost. And that I'm trying to minimize. So I hope that you can see the trade-off between these two objectives. I'm just going to go quickly to say that we can do this for any kind of data that you may have. So it doesn't need to be, say, tabular data. It could also be functional data, text data. I would also like to point out that the options for my counterfactual could be discrete options or could be continuous. So discrete option is when I choose, for instance, out of a data set. And it could be continuous when I'm, say, construct a synthetic individual. And things become a little bit easier if my classifier is a score based, so I can give you a little bit of more of an intuition, but again, I can reassure you that most of the machine learning models you work with, they are scores based, as you can see over there. So in terms of cost, and this I would like to stress because it's going to be very, very visual in a second in my slides, in my plots. In terms of my effort, I'm going to have a dissimilarity. So think about the Euclidean distance, for instance, very easy. But I'm also going to have a complexity. And this is important because the complexity is going to control how many features, for instance, is one way of measuring complexity. How many features I need to move to go to my contrafactual. So say I'm changing the salary, I'm changing the debt that I have to get my loan. So this would be, say, a visualization of 10 different contrafactuals for 10 different individuals. So 10 individuals for which you would like to increase the probability of getting the loan. And this is for the logistic regression. It's a very, very simple model to solve because you end up having a very simple constraint. And in case that you take the Euclidean and the zero norm, this would be a friendly solve problem that you can give to your favorite MIP solver. If I have an ensemble, it would take me a little bit of more time, but it can be done. And of course, different machine learning model, different contrafactors. Yeah, different machine learning model, different contrafactors, because you are basing your contrafactors on the machine learning model. In this case, it becomes a little bit of more work because to know, say, the probability of the contrafactual that I'm building, I will need to route, say, the individuals. And so this routing would need to be done across all the trees in my ensemble, and I could have many trees in my ensemble. Now, I hope that I can make now very clear why I want a group contrafactual analysis. And the reason why I want a group contrafactual analysis is because you have seen me giving you a plot of 10 individuals and giving you a plot of the 10 contrafactuals. And then these contrafactuals are free to change whatever features they want to do. I'm constraining the L0, but I'm constraining the L0 for every single individual. So I could be changing X1 and X10, and the next person could be changing X2 and X11, and so on and so on and so on. So globally, I could actually be changing all the features. And if I want to learn about my model, maybe what I want to make sure is that these contrafactuals are changing always the same features globally for all the contrafactuals. And you can see that now what I'm doing is just linking all these contrafactual problems that I have for each of the instances. So this is one of the reasons that I have for group, so detecting the critical features, but I have other reasons of diversity and other reasons like finding critical observations in my dataset. I'm not going to spend much time, but this is basically what is linking my individuals with my contrafactuals in a group setting. So I could be building a contrafactual for each individual, or for an individual, I could be giving, say, the option of several contrafactuals, because then the individual can decide the one that he or she likes. Or I could do, say, this prototyping, detecting critical individuals in the data set and making them contrafactuals for a group of individuals. So I hope you realize that with these 4 options that I have given to you, what I'm doing is creating different OR models to build group contrafactual explanations. And normally in contrafactual explanations, I decide the X, but actually in group contrafactual explanations, I also have to decide the assignment of contrafactuals to individuals. So I have also these decision variables relating to this assignment, and I hope this rings a bell, that it's sort of what you also do in, say, in clustering, in which you are trying to basically make groups of individuals. Now, in group contrafactual explanations, now everything becomes a little bit bigger because I have several individuals and I have several contrafactuals. So I have put an underline to model that. And I hope you realized that my cost function also becomes a little bit more elaborated, because apart from measuring the dissimilarity from me to my contrafactual, I also have to measure the complexity. And the complexity, I was talking before about you controlling, for instance, the number of features that you are using. But this was done at the individual level. What you can also do is to do this at the global level. So the complexity can now become 2 terms, which is the local sparsity and the global sparsity. For the same reason, I need to think when I do global contrafactual explanations, I need to think about, say, how I combine all these probabilities from all these contrafactuals. Do I look at the worst case? Do I look at, say, the arithmetic average or geometric average? So I'm just going to give you a couple of screenshots of a couple of group contrafactual models, and I hope the message will come across that I can learn from my model. So this is the first screenshot that I would like to give you, in which I'm building a contrafactual for every single observation. So I hope that you see there me having an S subindex. So it means that I have a lot of individuals that were, say, disappointed by the algorithm, that got a negative result. And for each of them, you want to improve the probability of belonging to the positive class. But I will now control the features that they need to change. And I will also control the features that I would need to change, but globally. So you can see me using a 0 norm in 2 different ways, so locally and globally. And now what I can do is, on the left, I can construct a contrafactual explanation. And of course, I don't pretend that you can read all these lines, but I guess you realize that I'm that there is a movement there, and that that movement is to do with the fact that I can use more or less features globally. So I'm controlling the third objective. So how many features I can use globally. And what I have is a lot of lines over there, because I have a lot of individuals in which I try to build my contrafactual explanations. And then what you see on the right of the screen is, depending on the number of features that I'm allowed to use, I will be choosing different combinations. This is a data set that is quite well known. It's the housing data set, and some of you will realize that some of the features that I'm using, they are very important if I will run a random forest. So basically, my counterfactual, my group counterfactual model is detecting also important features when building my model. I don't want to overrun today. I'm just going to show you a couple of things more, and I will leave it here. So I told you that I would maybe like to construct more than one counterfactual for the same individual. And I hope that you can see over here that I have 3 counterfactuals, and they are the 3 of them for the same individual. So you are basically giving the individual an option to choose for one of them. And to be able to construct this, you need a single model that can control basically the diversity of these counterfactuals. And finally, and this is one of the messages that we have in this paper, is building these group counterfactual explanations. Actually, the community will benefit a lot from the knowledge that we have from locational analysis. So in this case, we are trying to build counterfactual explanations, say 3 counterfactual explanations, but at the same time, we are grouping the individuals. And you can see the model that I have in front of you. You can see that I'm deciding to which group every individual is going to go. So I'm doing a kind of a clustering. And the objective function, it also resembles a clustering problem, but then I have additional constraints, these ones in which I try to make sure that the counterfactual is going to have a high probability, say, of belonging to the positive class. So it's a constrained clustering problem. If I would have 3 clusters, and then I hope that you can see now something different. Now I'm showing you the counterfactuals here at the bottom. So I have 3 of them. 3 of them. So what I'm hoping that you see is that the counterfactual is not so different from the features of the individuals in the group. So you have tried to be close to your individuals as much as you can. And that grouping was found by our OR model. Okay, so I hope that I have given you, say, a few models in which you can enhance transparency and fairness. I hope that with 1 or 2 visualizations, I have shown to you that actually you don't need to lose a lot of accuracy to gain, say, on fairness and explainability. And what I didn't show today to you is that you could do this not only in machine learning, but we also do work, for instance, in data envelopment analysis models, in which we are also trying to put this explainability layer. And what I have tried to say to you is that actually, I think there is plenty of scope for more of these models in which we can basically have control of this transparency and the fairness. And I know I went a little bit from one slide to the other, but all our work is it's on my ResearchGate entry. Yeah. So at this point, I'm going to stop sharing, and I think there were a few things in the chat, but I hope we can discuss, say, in person.
Thank you very much. That was absolutely fantastic and a complete whirlwind. Woo! So I know there are a couple of questions. One, and we've only got a couple of minutes left, so I'm going to have to be fairly quick on this. I did have one myself, but I'm going to skip that and go straight to somebody was asking about what do you mean by clustering in this context? What kind of clustering are you looking at? What sort of,
Yes.
how are you using clustering?
So I hope we are referring to the counterfactual. So I'm not referring at this point to clustering as, say, the machine learning task. What I'm saying is, if I have a machine learning model and you are trying to explain it through counterfactual explanations, sometimes what is valuable is to detect individuals from the data set that are in the positive class and you would like to be similar to them. So these are like benchmarks to our best practices or whatever you want to call it. So to detect those, you will actually be doing a sort of a clustering in the data set in which these individuals who got a negative answer will need to decide to which benchmark they would like to go. So the decision of the benchmarks and the decision of the allocation, that becomes a sort of a clustering model by itself. So I guess that what I'm trying to say is that clustering becomes a tool to give explanations.
So it's sort of, you're using anything that can give you what you need in terms of
I could use
segregation
k-means.
of categorization of groups, basically.
Yes, yes, yes.
Yeah.
But I have an extra constraint. So I cannot use a clustering off the shelf because I have an extra constraint that says, hey, my benchmark should have a very, very high probability of being in the positive class. If you are just happy that it's in the positive class, then it's okay. But normally you are measuring the probability of being in the positive class, very comfortable. So it's a clustering model with an additional constraint.
All right, thank you. That clears that up. Bala, I think you had more than one question in the chat.
Now, I was curious the idea behind to use sum of squared error on the linear example that you gave instead of root mean square error.
You mean for the counterfactuals?
No, not for the counterfactual. I think there was one slide where you were talking about continuous variable and you were trying to plot out uh, the error. I think it was IoT example that you were talking
Sorry?
about. The
Yeah.
IoT example.
Yeah.
Yeah. So I was just wondering why SSE was preferred over root mean square. Nothing big. I
Oh,
think.
no. Yeah. No. I could have put a different error function. Yes.
Okay.
So it's not context dependent. Yeah.
Yeah.
As a habit, when we do machine learning model, the habit is always to go with root mean square.
Yeah. So I could have put
No,
the
that's
root
okay.
with.
I was just
Yeah.
curious when I
Mhm.
saw something.
No.
So has anybody else got a question before I am going to put the one that I thought of to Dolores? Doing that 10-second count that us teachers have to do. Well, if you don't shut up, people don't put themselves forward. Okay, all right, then I am going to ask that one. In your very first example, you took a tree and you condensed it so that it was simpler and it had less to it. Was there an interaction with a user that made you think that's what we've got to do to it to make it easier for them to understand?
The interaction there, it was with no, it was an interaction all the time with the model. I don't know what kind of interaction you want, but I guess we could. So at the very, very end of the talk, I have talked about counterfactual explanations. So what we did, it was, okay, give me your, say, ugly random forest with many trees. And every time I have an observation, I'm going to construct a counterfactual. And we did that for all the observations. So what we did, it was to detect, say, frequent crossings of the decision boundary. Yeah. How many times you would like to change the age? How many times you would like to change the salary? How many times you would like to change the debt? And basically, what we did, it was to extract a lot of information from this crossing of the boundaries. And then, because it's a binary classification. And then what we did, it was to construct an optimal tree with the most frequent, features in which you would like to cross the boundary. But the information comes from the counterfactual. So I don't know which interaction you would like to have with the user, but we could have put in the construction of the optimal tree, we could have put something that is desirable to you.
You could put us in there, couldn't you? Anyway.
Yeah, because what we are doing is we are combining actually two things. We are combining the fact that we have these counterfactuals and is generating information about, say, features that you would like to change to go to the good side of the decision boundaries, but I'm also constructing an optimal tree with these features. So if you construct an optimal tree, you can put anything that you can model as a constraint or as an objective. I can put it in my optimal tree model, which you couldn't do, say,
it would
when
be
people.
really interesting to actually do a series of experiments with that, wouldn't it?
Yeah.
Get some real people in the room and start getting to mess around with it.
Yeah, because I mean, also another thing that I was trying to say is that, okay, you have the optimal model, but sometimes you don't mind to drop a little bit if you get this, say, intuitive thinking of the person you are collaborating with. So, but putting, say, the desirable properties into the model. Yeah. And this optimal trees, I mean, is one of the benefits. Of course, I mean, it's, if you want to construct an optimal tree, it has to be short. It cannot be long because they take a lot of time in terms of computations. But yes, it can be done.
That would be the next step for me. Is to do the messy bit where we bring it together with people and see how they contaminate the models. What they do to it.
It has its own risk too, and that's another kind of research, right? The manipulation of models. Yeah. So
absolutely.
Yeah.
Fantastic. Well, that's my interest area, and partly thanks to your encouragement, actually.
Yeah.
So, what have I got? There's a message in the chat here from Trevor Lee Cox. Do you want to ask that question yourself, Trevor? And unmute.
Yes. Good evening, Dolores. Thank you very much for a very interesting chat. I'm much more interested in the business side of things.
Yeah.
And I love the idea of group counterfactuals and the ability to be able to report back the quality of your particular model that you're generating. But I wonder, is there a way of actually identifying what are the significant variables that you need to track in order to ensure fairness, even before you start collecting the data?
I'm not sure in which direction you go, but everything, no.
Well, you seem to be restricted by the variables that you've actually got in your data sets right now.
Yes.
I'm talking about being proactive even before you start collecting the data for the data sets. Can you actually determine which are going to be important variables to collect, data variables to collect for a particular situation?
No, I don't think I can tell you. No. I don't think I can tell you in advance what would be, say.
Okay. All right, it was a bit of a left-wing shot anyway, but thank you. It was a very interesting talk.
No, I mean, what actually, another area of research that is important is I've been protecting today one group. So I've been focusing in protecting one group. And actually, another thing that is also important is how can you detect that there is no group that you are, say, discriminating against across different features and across different, say, discretization of the features. So if that helps, you were saying that I rely on features. Yes, I was relying today on having the sensitive attribute having defined to me, but another area of research which would be more combinatorial is to basically have a look and trying to figure out whether there is any group, not for my sensitive features, but for a collection of sensitive features that is under threat. And there I would not depend on having that features I was talking about. There I could do it for a group of features, of sensitive features.
Right. Well, thank you very much indeed. I'm going to just reply to Bala, but thank you. It was a really good chat. Thank you, Christina.
Thank you, Trevor. So I think now we've 9 minutes overrun, and Dolores is actually an hour behind us. So she's now at 6:30 in the evening. Thank you very much for cutting into your evening for us. And I'm just going to say thank you very much to everybody for coming. Thank you very much for Dolores for coming. Karen has put up in the chat that the recording should be available on the YouTube channel in the new year for anybody who wants to look back over it, because I'm sure there's some very interesting nuggets in there that we'd actually like to review as well. So once again, thank you very much, everybody, for coming, and we'll see you all at the next Analytics Network event. Thank you.
Thank you so much. Thank you.
Cheers. Bye-bye.
It has been a pleasure. Thank you.
Thank you.